Hello everyone, and welcome back to another episode of the Internet Computer Developer Journey. In today's episode, 5.3, creating a decentralized token swap, we're going to take a look at DeFi applications, particularly decentralized exchanges, and how we can create a simple token swap application that supports the ICRC2 standard. ICP enables DeFi applications through its unique design that includes complex on-chain computation. One of the most common examples of a DeFi application is a decentralized exchange, or a DEX, which is used to buy, sell, trade, and withdraw cryptocurrencies and other digital assets without a centralized authority that authorizes the trades, such as a traditional bank. Decentralized exchanges are extremely useful as they allow users to buy and hold cryptocurrencies, trade it directly for another token or coin, and then withdraw the tokens to be used elsewhere. So in this example, our simple token swap canister is going to swap all deposits for each of the users. So user A is going to have a balance of token A, and all of token A is going to be swapped for user B's balance of token B. And like I mentioned at the start of this video, we are going to be showcasing the ICRC2 standard. And if you need a refresher on ICRC tokens, you can check out the previous module 4.2 ICRC tokens. So before we get started, make sure that you have set up your developer environment according to the instructions in the previous module 0.3 developer environment setup. And then in a new terminal window, you're going to want to navigate into whatever your working directory is for the Developer Journey series if you have one. And then we're going to clone the examples repo and navigate into the ICRC2-swap directory. So we can see that I already have the examples repo downloaded locally, so I don't need to run git clone, but I will run cd examples motoko ICRC2 swap. And then once we are in this project's directory, we can see that we have a dfx.json file that has our project's configuration in it. And then we have this source file that has the code for our backend canister. And this backend canister is going to have two Motoko files that make up the backend functionality, a main.mo file and an icrc.mo file. The main.mo file is the token swap canister source code, and the icrc.mo file is a module containing types that are imported into the main.mo file. This project also includes a test subdirectory that contains TypeScript files that are used to test the token swap canister's functionality. Now, if we take a look at the dfx.json file, we can go ahead and open this in our IDE of choice. So I'm just going to open up VS Code, and I'm going to open my examples folder, Motoko, and then ICRC2 swap. And then I'll make this a bit bigger. And so in our dfx.json file, we can see that we have three canisters defined. One is a canister called swap. This is going to be our backend canister. And then we have two additional canisters. One is called token A and one is called token B. Both of these are pulling their candid and wasm files from the DFINITY public repository. And these are both just going to use the ledger files for the ICRC1 ledger. And if you notice, we don't have a front-end canister defined in this project. We will be interacting with this project purely from the command line. We will not have a user interface that we'll be using. So both of these token A and token B canisters are pulling the latest modules for the ICRC1 ledger, and they will be used to create ICRC2 tokens. The latest version of the ICRC1 ledger does support ICRC2. So now if we go into our backend canisters source code, so source/swap/main.mo, we can see that we have a rather long piece of code that is going to set up the swap capabilities for our example. We're going to start out by importing a series of libraries from the Motoko base library, and then we're going to import the ICRC type definitions from that icrc.mo file. So the swap canister is the main backend canister for this example. To simplify the example, we're going to configure the swap canister with two tokens, and that's going to be token A and token B. We are going to set up some variables that track the deposited per user balances for token A and token B. And then because try maps, the data type that we used to define these variables, because they are not directly storable in stable memory, we need a location to store the data during canister upgrades. So then we are defining a second variable that is a stable variable called stable balances A and stable balances B, and these are just going to be the places to store these balances during upgrades in the stable memory of the canister. Then we're going to define the public function balances, which is a simple get function to check the balances of all users, and it's primarily used for debugging. Then we're going to define the public function deposit. This is going to accept token A and token B as deposits. The user approves the transfer for token A.icrc2 approve. Once a user deposits their token, they're going to use the swap_canister.deposit, and then these deposit handlers show how to safely accept and register deposits of an ICRC2 token. We also need to load the fee for the token. The user can pass a null fee, which means use the default, so we need to look up the default in order to correctly deduct it from the balance. Then the logic for the actual transfer is defined here, where we have different parameters such as the spender subaccount, the account that the transfer is from, the account that the transfer is to, the amount, the fee, the memo, and the time that this transaction was created at. And then we have some logic to check if the transfer was successful. If it failed, there's no cleanup to do since the state of the canister will not be changed, so the error can be returned as a plain error. Then from this point in the code, we need to make sure that this deposit function does not fail. If it has failed, the transfer of the tokens would be complete, meaning that we would have the user's tokens, but we would not have credited their account, so the canister would not know if it had received the user's tokens. If the function can fail here at this point in the function, then you should consider either moving that code to a separate action later or have error handling code that refunds the user's tokens. So then we define the logic to credit the sender's account and then return the block height of the transfer. Next, we are defining a public type for a swap error. This is left as a placeholder for future implementations in case the swap function could fail. Next, we are going to define the public function swap. This is the logic that exchanges the tokens between two given users. So for example, there is no clever swap mechanism. It's simply going to swap all deposits for the two users, even allowing anybody to perform the swap, not necessarily one user or the other. Designing a useful and safer swap mechanism is left as an exercise for you, the developer, for this proof of concept example that is not within the scope. So this function is going to swap user A's full balance of token A to user B, and then user B's full balance of token B is going to be given to user A. Because both tokens were deposited before calling the swap, we can execute this function atomically. To do that, there must be no await calls in this function. If there were await calls, we would need to be careful about the order that we update any internal state variables. If this function were to update some state variables, call await, then fail before updating others, it could leave the canister with an inconsistent internal state. So by making this function atomic, it makes it safer because either all of the state changes applied in this function will be persisted or all of the state changes will be reverted. So here we define the logic to give user A's token A to user B. It adds the two users token A balances and gives all of it to user B. Then it has logic to do the same for user B's token B. Then we define some public types for withdraw arguments and a public type for errors regarding withdraws. So if there is an error with the transfer itself or if there are insufficient funds, these are two possible errors that can be returned. Next, we define the public withdraw function. This allows users to withdraw any tokens that they hold, and these withdraw handlers show how to safely set outbound transfers of an ICRC1 token. So here we define the logic to load a fee from the token. A user can pass a no fee like they did in the previous function that we defined, or they can pass a no fee which uses the default. And then it checks to make sure that the user's balance is sufficient and that they can actually withdraw the tokens and also cover the fee. Then once they are withdrawing the tokens, we need to debit the sender's account. Due to the asynchronous nature of ICP, we do this step first. And by debiting the account first, we can ensure that the user cannot withdraw more than they have. If they were to perform the transfer, then debit the user's account. There are several ways that somebody could maliciously exploit this, and it could lead to a loss of those tokens. Then we perform the actual transfer to send the tokens and then check that the transfer was successful. If the transfer failed, we need to refund the user's account, and that is so they do not completely use their tokens, and then the withdrawal can be retried. And if the transfer was successful, we need to return the block height of the transfer. Then we define a private function of which balances. This checks which token we are withdrawing and configures the rest of the transfer. This function will assert that the token specified must either be token A or token B. And then lastly, this code defines a pre-upgrade and a post-upgrade hook that can be used for upgrading the canister. And so next, let's just take a brief look at the icrc.mo file. So this is defining a series of types that are imported in the main.mo file. And so it defines this module, ICRC, and it has public types of block index, subaccount, timestamp, tokens, token index, account, transfer argument, transfer error, transfer result, metadata value, approve arguments, approve error, approve result, allowance arguments, allowance, transfer from args, transfer from result, transfer from error, and then the public type actor. And so these are all used throughout this main.mo file. So now going back to our tutorial, if we scroll down, now that we've taken a look at the code, we are ready to deploy it and start to use it. So we'll run dfx start clean background to start dfx, and we can see that I already have dfx running. Then we are going to create two new identities, one for user A and one for user B. So dfx identity new user A. And for me, this identity already exists, but we'll run the second one as well. dfx identity new user B. And this also already exists for me. And then we are going to export these as environment variables. So we'll use export user A equals dfx identity get principal, and then the identity is user A. And we'll see that I need to authenticate locally for this. And then we are going to run the same command, but for user B. So I'm just going to use the up arrow to get that last command in my terminal and then change the A's to B's. And then it's going to ask me to authenticate that again. And so now we want to set our dev journey identity as the owner variable. So DFX identity use dev journey. And then I want to export owner equals DFX identity get principal. And so now we have our environment variable set up. And so now if we want to deploy token A, we need to deploy the token A canister and pass a series of arguments to the canister to create that token. So here we're going to use this long DFX deploy token A command and then pass the argument that creates a token with token name token A. The symbol is going to be A. The owner is going to be our owner environment variable, so our developer journey or our dev journey identity. The initial balance of these token A tokens are going to be deposited into user A's account, and we're going to have 100 billion. And then the metadata for this token, it's going to have a transfer fee of 10,000. It's going to have some archive options, and then it's going to have ICR22 equals true. So it's going to be an ICR22 token. So I'm just going to copy this whole command and paste it. And then we're going to see that the canister token A is going to be deployed, and it's going to be initialized with these arguments to create token A. And we can see that it was deployed successfully. And so now we can scroll down and do the same for token B. So this is going to look almost identical, but instead of having the owner principal be user A, it's going to be user B. So we're going to copy this and paste this and run this command as well. And we can see that that was successfully deployed. And so it used the same general setup as token A did. And so next, let's export the token canister IDs as environment variables so we can use them in further commands. So we're going to use export token A equals DFX canister ID token A. And then we're going to do the same for token B. So I'm just going to use the up arrow again to get that last command and just change the A's to B's. And so now we want to deploy the swap canister. So we want to pass the token canisters as arguments to the swap canister. So we're going to do DFX deploy swap and then pass the argument of token A equals that canister ID that we just saved as an environment variable for token A, and token B as the environment variable for token B. So I'm just going to copy this command and paste this, and we can see that now the swap canister is being deployed. And so now we have all three of our canisters running, swap, token A, and token B. And then we are going to export the swap canister ID as an environment variable as well. So export swap equals DFX canister ID swap. So now we need to deposit the tokens into the swap canister. Before they can be swapped, they need to be in that swap canister so that the swap canister can swap them for one another. And since the tokens in this example use ICRC2, this is a two-step process. First, the transfer of these tokens must be approved. So in this example, we are going to approve user A to deposit one of token A, and we're also going to include a little extra to cover that transfer fee. So we're going to use DFX call and we're going to pass in identity user A. Then we're going to be calling the token A canister, and we're going to be calling that canister's ICRC2 approve method. And we are going to pass in the amount that we want to approve to be spent, and then have the principal that we are approving for the spending to be the ID of that swap canister. So we are telling the token A canister that, hey, we want to allow the swap canister to be able to use this amount of tokens. So we're going to just copy and paste that command into the command line, and we can see that it returns OK equals 1, so that was successful. And then we're going to do the same for token B. So we are telling the token B canister that we would like to approve the swap canister to be able to spend this amount of token B tokens. So now that both of these tokens have been approved for use by the swap canister, we can deposit them into the swap canister. So we're going to use DFX canister call. First, we're going to deposit the token A token. So we're going to use identity user A. Then we're going to call the swap canister, and we're going to call its deposit method. And then we're going to deposit the token A tokens, and we are depositing them from user A. So we're going to copy and paste that. And we can see that that was successful. And then we're going to do the same for token B. And so that was also successful. So we had to approve them because these are ICRC2 tokens, and ICRC2 tokens include this transfer approve functionality that is similar to the Ethereum network's transfer approve functionality for ERC20 tokens, where you are able to allow another user or account to spend X amount of tokens that you hold or have custody of. And so what we did here is user A and user B both had balances of token A and token B, and they approved the swap canister's identity to spend token A and token B on their behalf, or transfer them on their behalf. So now that we have these successfully transferred into the swap canister, we can call the swap method of the swap canister to swap user A's tokens for user B's tokens. So we'll go ahead and copy and paste that command and do that swap. And then to make sure that these balances are now swapped, so now user A should have a balance of token B and user B should have a balance of token A, we can do DFX canister call swap balances to view the balances for each. And we can see that we have right now just records of the principal and their balance of 100 million for both of those. So now that the swap is complete, users can withdraw their newly received tokens out of the swap canister. So first, to withdraw user A's balance of token B, we want to use DFX canister call identity user A, and we want to call the swap canister's withdraw function. And then we want token to equal token B. And then we are pulling it from user A's balance of token B. And then the amount is going to be a little less than 100 million, since we want this value to be minus the transfer fee. So we'll copy and paste this to the command line, and we can see that this was successful. So we were able to withdraw token B from user A's balance, further validating that the swap was successful. And so now we're going to do the same for user B. We are going to withdraw token A from the balance of user B. And we can see that that was also successful. So then, to confirm that everything worked as expected, we can check the token balance for each user. So first, let's check user A's balance of token A. They should have 9 they should have 998.9998 of token A. So let's take a look. If we use DFX canister call token A, ICRC balance of user A, the principal, and we can see that that returns the expected value. And then we can do the same for user B's balance of token B. And we can see that that was successful as well. So that's going to wrap up today's episode of the Internet Computer Developer Journey. If you enjoyed today's episode, please be sure to like and subscribe to the DFINITY YouTube channel to stay up to date with new episodes of the Developer Journey and other educational series here on YouTube. You can also reach out on the ICP Developer Forum or ICP Discord server if you have questions or want to connect with other developers on their developer journey. That'll wrap things up for today. Take care.